Hi, this is Professor Rasmussen. This is another example of a maximum transfer or max power transfer problem. This is 8.57 from the book. So in order to solve this circuit, you want to determine VTH, which is going to be the Thevenin equivalent, and the RTH, which is going to be the equivalent resistance. So redraw the circuit or copy it, either one, and then need to remove Z load to find, we're first going to look at finding VTH. So I've removed Z load, and then I want to put in a open here of A and B. And across A and B is where I want to see VTH. I also noticed that on the left, there's a node here. And then of course there's a node here and a node here on the right. For this left side, I noticed that it's connected at that node to the other side of it is at ground. So here is at ground. So it does mean that node V will be in that blue area that's highlighted. VTH is going to be all this node here. So VTH and then to ground. So that node there, I can just call VTH. And on this node here, it doesn't have any differentiation. And so I want to just call that a new node name. So I'm going to call this Vx as an unknown. And this node is VTH and this node is V. And I'm going to label those a different color. So bright purple. Okay, so Vx, VTH, and then this whole node over here, all of that blue wire is V. So now when I do node voltage, say I want to do a node voltage, I'm only going to do node voltage at VTH and Vx because the other node on the blue side is going to be V, which was given as 30 angle 60 degrees, which can be written as 30 EJ to the 60 degrees. So let me do at, let's start with VTH. So at the VTH node, I only have the current going to the left, and then I have the current going to the right. Notice that because the node or the VTH is open, there's no current going through that. So this is a floating wire here, and so zero current goes through that one. So expressing the current going out of VTH towards V, I have VTH minus V over 5. And then VTH minus Vx over minus 4J. And that equals 0. And then at Vx, I get this current here, which is going to be Vx minus V over 20. And then this current here, notice that it's opposite the current that's purple. So I can either write that term and do a negative of it, which that was expressed here, VTH minus Vx over minus 4J. Or I can just rewrite it. I start with Vx, and I add all of mine because I'm going outwards from the node. So Vx minus VTH over minus 4J. And you can see that that is the same, just a minus of that. And then the current going down is going to be Vx minus 0 over the summation of those. So 10 plus 6J equals 0. So now I want to write these as far as reordering them. So I'm going to call this equation 1, this equation 2. So for my equation 1, I'm going to put this into matrix form to solve it. And so I'm going to define VTH as my first variable. So I can randomly pick that value. So 1 over 5 minus 1 over minus 4j, and that will be my VTH terms. And then I'm going to use Vx as my next variable. So then that's a minus over a minus, so plus 1 over 4j, Vx, and then my V over 5 comes over to this side, and my V is 30 EJ 60 degrees over 5. My equation 2 is going to, again, I keep consistent with the ordering of which variables I'm lumping together. So VTH will be first, which gives me a minus VTH over minus 4j, so 1 over 4j. VTH, and then Vx is the next variable, so that gives me 1 over 20, 1 over minus 4j, and then a 1 over 10 plus 6j, Vx. And then the V over 20 goes over to the other side, and again, V is 30 EJ 60 degrees. So now I want to write this into matrix form. And so I can do that and get values for so I define my A as the first equation is 1/5 plus minus 1 over 4j or 1 over minus 4j, and then 1 over 4j, and then on the second row it's going to be 1 over 4j VTH, and then this whole term, which is that one. And then I defined a X as the value to find 60. So MATLAB always does radians as the default. So I need to convert 60 degrees to radians. So I do that by taking 60 times pi over 180. So that's why I have this X here. Now that is now in radians. And so I can do my B side is going to be 30 EJ to that X, and then over 5. And then the second row will be 30 EJX over 20. And then solving that, I do the inverse of A times B. So just invert that A matrix. And that gives me two values. The first value, again, is defined by the first variable that I put together for the A matrix. So in this case, this will be the value of VTH, and this will be the value of Vx. And then for VTH, to find the power, I'm going to need to know the magnitude. So in order to do that, I can change from these Cartesian coordinates to polar. And so that's going to be this first line, 10.4613, and then 19.3981. And this gives me then theta, which is the angle in radians, and then r is going to be the radius, is 22.039. So this is the value I'm going to use for the magnitude of VTH when I'm finding the average power. So the next thing I need to do is find Thevenin equivalent, includes, so I found VTH now, I need to find RTH. So I remove the independent sources and I remove the load. I replace the source with it was a voltage source, so it's voltage equals 0, which means it's going to be a wire. And then A to B of where the node is. And now I need to find a pathway from A back to B. So as I do that, I'm going to color code these different nodes. And so I'm going to do that one red since it won't highlight. So I have blue, and then I'm going to do purple. Actually, I should probably stay with the same coloring. So I did red up here for the middle one. And then purple on this side. And then blue. I'll just color this blue. Okay. And so my pathway, as I go through this, I notice I go up and then I have to split to the right and split to the left. So remember that when you split, that is a parallel form. So here I'm going to have that Z is equal to one branch, which the B side is all blue. So one of the branches, R1, will go right to blue. And then I notice on the right, it has to go through the ZC. And then it splits again here. So that split means that those two are in parallel. So it's going to be a plus 20 in parallel with ZL plus R3, and that whole amount, these two together, which is series, are in parallel with 20. And then that gets me back to blue on the other side. So this is going to be my equation for ZTH. And so I could write this temporary Z1 term as just, let me put in these values. ZL was 6J, R3 was 10. And so this is going to be, I'm going to do, here. I'm going to write this parallel form as a Z1. And so that becomes 1 over 20 plus 1 over ZL is 6J and R3 is 10. So 1 over 6J plus 10. And then using that, my ZTH can be written as 1 over R1, which is 5, plus 1 over, and then ZC is minus 4J plus Z1. So I can then manipulate this or do algebra on it if I want, or use an online calculator to do the complex math here. And that gives me the 2.9755 minus about 2.4J. So now for the maximum power transfer and the average power. The maximum power transfer is just going to be, ZL is going to be opposite this ZTH, or complex conjugate of this ZTH. So the real part is left alone, and then it's a plus instead of a minus 2.387J, 0.2387J. So there is my load impedance to get maximum power transfer. And then my power average max is going to be 1 over 8. And then this is where I use that 22.039 squared all over. RL is the real portion. of the load, Zia. So I use the 2.98, and that ends up giving me approximately 20 watts. Thank you for watching.